The theme of Nuremberg series this week was billiards. We had 2 lectures by Sergei, and we're continuing with the 2 lectures of Sergei Tabachnikov. Today's lecture is, however, standalone. It's open to the general audience, the colloquium talk. And I'd like to introduce Professor Tabachnikov to you again. You and yesterday, Edward did a wonderful introduction, and I'm not going to be able to match. So Professor Tabachnikov is a specialist in billiards and projective geometry and geometry at large. He's a former deputy director of his term and emeritus deputy director of his term. He's in the editorial board and editor-in-chief of several journals, and a fellow of the American Mathematical Society. So today's talk will be on billiards in Conics Revisited. And please.
Thank you very much. Again, I'm honored to be here. And with this talk, I take some risk. On the one hand, I'll be talking about things which, in part at least, have been known for about 2,000 years, maybe a little less. On the other hand, I hope that everyone in the room will see something new for you. And also, in spite of the maxim that a talk should contain only one proof, I actually plan to maybe present 2 or 3, or maybe 4, if I'm in luck, to compensate for the elementary nature of the subject. Okay, so let's see how this works. Maybe that, and yeah. There's no, oops, that's too fast. Okay, start again. I don't really need to remind you what billiards are. It's the 4th talk in the series, but still there is a slide. On the left, you have an oval. So I'll be talking only about billiards, mostly about billiards in ellipses, but this is a convex domain. Of course, it's an ellipse. I can't draw any other convex domain. It's the system which describes motion of free particle inside this domain. It goes with constant speed along a straight line, hits the boundary, reflects according to the familiar law, angle of incidence equals angle of reflection. And if you prefer, you can think of this as of the boundary as an ideal mirror, and trajectories are rays of light, and this is reflection in the geometric optics approximation of a much more complicated physics process. On the right, you see again a billiard table and a red curve. It's called caustic, and the definition of caustic is it's a curve such that if a ray of light, I will mostly use optical language, if the ray of light is tangent to this curve, then the reflected one is again tangent and forever so. And the word caustic means burning, and it's certainly a very classical object. One of the very first questions to ask is, given a Birkhoff billiard inside a convex domain with a boundary which has positive curvature, do caustics exist? And this is a KM style, Kolmogorov-Arnold-Moser theory style question. And the answer is yes. There are caustics near the boundary, and they accumulate toward the boundary. The measure relative measure goes to 1, and this is Lazutkin's theorem, which is quite old. It's 1973. So what you see here is one such caustic, and if a billiard table is generic, then if you go inside, caustic may not be there. There are results starting with Gutkin and Katok describing that how caustics cannot exist if you go inside. But in my talk, they will exist because I'll be talking about ellipses mostly. But before doing that, I need to say a few words about symplectic, or if you wish, area preserving. I'll stay in dimension 2. So symplectic simply means symplectic structure simply means area. Although what I'm saying here is quite general. So the space of oriented lines or rays of light has a remarkable symplectic structure. In the plane, how do you describe an oriented line? You choose an origin, this point O, and a line has a direction, which is denoted by alpha here, and it's a point on a circle, directions, angles mod 2 pi. And also there is a distance, sign distance from the origin, and the sign is given by this corkscrew right-hand, left-hand rule. Anyway, the picture says it. And in these coordinates, the area form dp d alpha is the one I mean. And actually, this picture is multidimensional as well, and it's much more general than that. Any Riemannian manifold, if the space of non-parameterized oriented geodesics happens to be a manifold, that manifold is symplectic. And this is even more general than that. One can consider Fieldsman manifolds and so on. But again, these generalities are just for information. In my situation, we are in the plane, and the metric is Euclidean. Although maybe at the end I will say something about other metrics. Okay, so now the main character of today's talk, ellipse and billiard in ellipse. So this picture I stole, I think, from Colossians paper with permission, of course. Colossians 17. Okay, so let's see what we see here. This is an ellipse. There are several orbits shown here. They are color coded. There is an orbit which is green, which is close to the boundary. There is an orbit which is blue, which is not that close to the boundary. Both of them have caustics. They are tangent. The green one is tangent to this curve. The blue one is tangent to this curve. Then there is an orange trajectory. This passes through foci, and this effect, which you all know, and actually the Greeks also knew, that if you shoot a billiard ball from a focus, then it will reflect to another focus and continue like that. Actually, the dynamics is not integrable at all. I first time used the word integral, but I'll be talking about integrable all the time. Actually, if you iterate this, the trajectory will converge very fast, exponentially fast to the great axis of the ellipse, which is hyperbolic behavior. And then there is this purple trajectory, which is also tangent to something, as you see, and this something is hyperbola. I didn't say it. So the caustic, which is green, the caustic, which is blue, they are confocal ellipses, and this is confocal hyperbola. They all share this two red foci. So that's what this system is, and I promised you several proofs, and let me prove the first result, because it's very easy. All proofs will be simple. Okay, so what am I proving? Let's actually get back. I'm proving that the billiard inside an ellipse has a foliation on caustic, which consists of confocal ellipses. I will not say anything about hyperbolas, but that's another foliation on confocal hyperbolas. So everything is covered twice by confocal ellipses and confocal hyperbolas. But let me explain why this is so, because the algebra of it is very simple. So here's our ellipse. A is self-adjoint, well, symmetric 2 by 2 matrix. Parenthesis means scalar product. Ellipse is given by this. I didn't write x squared over a squared plus b squared over y squared over b squared equals 1. That's a shorthand for that. And here is the conserved quantity. So this is an ellipse. I characterize trajectories by two numbers. One is a point on the boundary, and another is a unit vector which has inward direction. So this defines a trajectory. It goes like this. XU goes to YU, and then reflection happens at this optical or elastic reflection, and YU becomes YV. So the map takes XU to YV. And here is a claim, AX.U equals AY.V. This is a conserved quantity integral, and an exercise for the audience is to see that this integral actually does what I said. It describes confocal ellipses, or confocal conics, to be precise. This I will not prove, but I'll show why this is an integral. It has a name, Joachim Stahl integral, and although I am in dimension 2, but this holds in any dimension. This integral exists in every dimension. If you really want to study billiards in high-dimensional ellipsoids, they are also integral. They have many integrals, but this integral is always there, and it's the easiest one. It's linear in momentum. Okay, so here's the proof. A is self-adjoint or symmetric, so we write ax plus ay dot y minus x, and a little calculation shows that this is 0, because axy equals ayx. And so axu equals ayu. That's 1/2 of what we need. And the second half is here. The normal to an ellipse, to the conic at point y, is given by that ay. And ay, the reflection law, is orthogonal to u plus v. That's what I write here. Ay dot u plus v is 0, and this means that. And if you can compare the two, this and this, we get this. End of proof. Promise, all proofs won't be harder than that. Okay, so I said it holds in every dimension. Oops, what? Sorry. All right, now integrability. So what integrability means, of course, depends on whom you ask. But in our situation, at least what it means is that the phase space, what you see here, is a phase space for a billiard. So if you want to use optical picture, then what you see is the set of oriented lines which intersect a given ellipse, and this phase space is foliated by curves. Each curve consists of oriented lines which are tangent to one confocal ellipse. Then there is this special singular curve. This consists of those lines which pass through one of the two foci. And then there are curves inside these eyes. These are lines which are tangent to a fixed confocal hyperbola. And these 2 points, they correspond to a short periodic trajectory, which is vertical axis of the ellipse, as the way I showed you. So let's think about this invariant curve. So each curve here is invariant, consists, according to the previous theorem, consists of billiard trajectory or rays of light, which are tangent to a fixed confocal ellipse. Particular case, very elementary again, the case of Arnold-Reville theorem from the theory of completely integrable systems, does in this situation the following. There is a way to introduce coordinates on all these curves such that the billiard transformation, which takes one point of the curve to another point, is in this coordinate just parallel translation. X goes to x plus constant. Constant depends on the curve. And the way it's defined, it's geometrically very clear. What do we have? We have invariant area form. Remember this dpd alpha, which I introduced on the second slide, I think. And we have this invariant foliation, which is invariant fiber-wise. Each curve is invariant. So we can use area between curve and a nearby curve to use it as a coordinate on a curve. So if I want to measure the length of a segment here, I actually measure the area above this piece of a curve and nearby curve. Okay, so in the limit, when this distance goes to 0, you need to divide by this epsilon, take a limit. What you get is a coordinate. And now our map preserves area, preserves the curves, and so preserves the result of this construction. This measure is preserved, and one-dimensional map which preserves the measure is parallel translation. X goes to x in this coordinate. X goes to x plus constant. So this is a particular case of much more general theorem, which is multidimensional, but that's enough for many applications. And now I will start showing you applications. Okay. Last try, and then I'll go to buttons. I don't know what's wrong. Maybe right hand would be more efficient. Okay, the first corollary is a classical result of projective geometry, Poncelet Porism. So this is Poncelet, and this is his theorem. Poncelet, by the way, discovered this when he was prisoner of war in Russia. That was 200 plus years ago. He participated in the Napoleonic War, was wounded almost mortally, but he didn't die, and he was taken as a prisoner, and he participated in a foot march from Western Russia, from Smolensk to city of Saratov on Volga River, survived this, although many prisoners did not. And he spent more than a year as a prisoner of war, but it was 19th century. It was not 20th nor 21st century. So they actually could not only survive, but do mathematics there. Officers didn't work in this POW camp, and they had time to do what they wanted. They could even practice in fencing, believe it or not. Those were the times. So Poncelet was a graduate of École Polytechnique. His geometry instructor was Monge, and he started with trying to recollect, to recall everything he was taught, and then he continued. And he had notes, and when he returned after the war in 1813 back to France, he started to work on a book, which was published several years later, 1828, maybe. I don't remember the year, but it was based on his Saratov notebooks, and this was one of the theorems he discovered here. So what do we see here? These are two ellipses, outer and inner one. They are not confocal yet, but I will make them confocal in a second. But the theorem, the game is take a point on the exterior, you draw a tangent line to the interior until you get back to the exterior, and then you continue. So if you play this game, you either come back or not. If you come back, as this picture shows, after 5 steps, the claim is that you will come back after 5 steps and making the same number of turns around. So here is 5-2. You go around twice, and it is 5. There is a dichotomy. Either it closes up after n steps and p times around for every point, or it does not for any point. That's Poncelet Porism. It's probably the most beautiful theorem of projective geometry, elementary projective geometry, at least in my opinion. And how to prove it, how to deduce it from billiards. So first of all, it's a projective statement. The only things involved are points, lines, connecting points with lines, tangency. So if we apply projective transformation, the theorem remains the same. And there is always a projective transformation which takes these two nested ellipses to confocal ellipses. And then we are back to and then we are back to the following picture. This picture, which says that the billiard transformation, now we're talking about billiards, since we have confocal ellipses. One is the actual boundary of the table, another is caustic. And we know that the map, which takes points to points, is actually parallel translation. Parallel translation has this property. Either its orbit closes up and then all orbits close up with the same period, or it does not. And that's precisely the statement of Poncelet Porism. Okay, next geometrical consequence. I'm sure that everyone knows Poncelet Porism, but this may be new to some, at least to some people. The next statement is that if we have two confocal ellipses as two billiard tables, boundaries of two billiard tables, we can consider two games, billiard inside one and billiard inside another. And then for trajectories which intersect both, we can consider composition. We can play one game and then the other game, composition of maps T1, T2, or in the opposite order. And the claim, a theorem, is that they commute. And this picture is precisely illustrating that. So this is the incoming trajectory. It reflects in the inner ellipse and then in the outer ellipse. Or it first reflects in the outer and then in the inner. And you see that the result is the same. So it's computer proof, but I also will give you mathematical proof. And mathematical proof would be, again, the same magic of Arnold-Liouville theorem. So you remember, I will not risk going back two slides, but you remember this phase picture with foliation on invariant curves. Now, the invariant curves, what are they? They correspond to confocal ellipses, but confocal ellipses are caustics for all confocal ellipses. It's the same system. So this coordinates, which I introduced using area form, actually is associated with confocal ellipses no matter what is the boundary of the billiard table. It's the same coordinates. So in other words, given an ellipse in the plane, the all confocal ellipses, each confocal ellipse carries a coordinate system which has the property that billiard reflection with respect to any other confocal ellipse, it should be outer, of course, is a parallel translation. The actual constant in this parallel translation depends on which ellipse you choose, but they all are parallel translations in the same coordinate system. And parallel translation commute, of course, and that's precisely what you see here. Okay, so let's consider a particular case of this picture when the incoming trajectory actually starts in the focus. That's this picture. Imagine that you don't have this ellipses in this picture, but you only have this geometric drawing, which consists of 1, 2, 3, 4 lines, four segments, and how many? 6 points. Okay, but you know what ellipse is? Ellipse is a locus of points such that sum of distances to foci is fixed. So if you don't know that these ellipses are here, then you still can interpret this picture as the most elementary problem of elementary geometry. This is a name coined not by me, of course. Yeah, I don't remember. Seeing a moment, I'll remember later who coined this description, this name. But here is a theorem. AC plus CB equals AD plus DB, if and only if AE plus EB equals AF plus FB in this picture. Challenge for you, prove it by high school mathematics. Okay, let's continue. Now I need to introduce string construction. So string construction is a way to reconstruct a billiard table. It's not necessarily conics. It's true for every convex curves. It's a way to reconstruct a billiard table from its caustic. So what you see here is a caustic, and we don't know the billiard table yet, but we can reconstruct it and actually a whole one-parameter family of them. And this is done as follows. You give yourself a non-stretchable string of fixed length, and you wrap it around. You wrap it around like this, and then you move this free point, keeping this string tight. And the locus of this free point traces a curve, and the claim is that this curve is a boundary of billiard table for which this is a caustic. In other words, the claim is that these two angles are equal in this construction. And the proof is, again, elementary. This is something I think should be in calculus books, but maybe it was 100 years ago, not today. So here's the proof. Choose a point on the other side. The argument will not depend on the choice of this point, really. And consider two functions of a free point x outside of this ellipse. One is distance from x to O going around one way. Another is distance from x to O going around another way. So what are gradients of these two functions? Well, clearly they are unit vectors which have directions along the tangent segments, right? It's tautologically so. Okay, now the string of fixed length has these two functions, sum of these two functions equal to constant. The gradient of sum is sum of gradients, so sum of these two unit vectors will be a non-unit vector like this. And of course, gradient is perpendicular to level curve, which is the curve given by string construction, and that's the proof. Sum of two unit vectors perpendicular to that, that's equivalent to this angles being equal. There is a classical geometrical theorem, Graves' theorem, which says that if you start with an ellipse and do the string construction, then what you obtain is confocal ellipse. And this, again, what you already know from a billiard interpretation of it. We can actually introduce coordinates outside of an ellipse. So start with an ellipse. As I already tried to convince you, an ellipse has a particular coordinate system which is related to billiard translation. So that billiard reflection is a translation of that. There are certain coordinates. So gamma is an ellipse, S and T are two values of this coordinates. Given a point outside, I draw two tangent lines and two tangent segments, and the tangency points have coordinates with respect to this coordinate system, S and T, and I use this pair S and T as a point outside. So again, as a reminder, two gradient and sum difference of this two angles. So in this coordinate system, confocal ellipses are given by the condition that difference of two parameters is constant, and confocal hyperbolas are given by a similar condition that the sum is constant. This I'm not proving. I don't want to prove every single. I already proved maybe 3 or 4 things, and there are more proofs to come. But trust me, this is also true. Actually, it follows from the fact that these two purple vectors are perpendicular and confocal conics are perpendicular. And the billiard reflection in a confocal ellipse in these coordinates is given again by the parallel translation, and billiard reflection in confocal hyperbola is given by a similar formula, but there is a minus here. So it's an involution. Okay. So we have these coordinates in the exterior of an ellipse. And now I will continue using this to prove more geometrical results. This one is Ivory's lemma. So it's again about the time of Napoleonic Wars, but he was Scottish, so he was not in Russian captivity. Ivory was a physicist, and he studied the potential of well, there are two formulations. I think one would be you consider an ellipsoid which is made of metal, and you drop liquid on it, which consists of charges, electrons, and they distribute somehow. And then you ask about potential outside. Or you can think of gravitational potential of an ellipsoid with certain density. Density is actually proportional to the volume between ellipsoid and mathetic ellipsoid. So Ivory studied this problem and found the description of this potential. Equipotential surfaces are confocal ellipsoids, but the crucial geometrical lemma is what is called Ivory's lemma, and its two-dimensional version is what I'm going to discuss. What you see here, again, these are two foci, these are two confocal ellipses, and these are two confocal hyperbolas, and they make a quadrilateral. And the lemma is that the diagonals of this quadrilateral are equal. It's a remarkable geometrical effect. I learned it actually a long time ago from Vladimir Arnold, and he complained that he didn't know a geometrical proof of it. And somehow in my back of my mind, this question stayed for 30 years maybe, or 40. But now I want to deduce it from billiards. I don't know whether Arnold would be happy with this proof or not, but it's possible to do. So let me explain how this goes. Here's what I want to do. As a warm-up, suppose I'm totally crazy and I want to prove that two diagonals of a rectangle have equal length. After all, that's what I want to prove. Two diagonals are. Okay, so of course, this does need to prove, but I want to prove it using billiards, and that's how I do it. First of all, I extend billiard trajectories to trajectories which enter right angle exactly. So I will extend it in such a way that they just go back along the same line. And the reason it makes sense is that if you consider nearby trajectory, it will make two reflections, but it will exit in a parallel direction. So now it's okay to do that. And here is my rectangle, and here are several four-periodic trajectories. So we have one parameter family of four-periodic trajectories. They all have the same perimeter because trajectory is given by variational principle. We have a function which is constant on this curve in the space of trajectories. Variational principle says that the differential of this function vanishes. It means that the length remains the same. And of course, this family interpolates between one diagonal and another diagonal. They all have the same perimeter. So I proved that two diagonals of rectangle have the same perimeter. It's not the easiest proof, but that's what I want to repeat now in the curved situation of Ivory lemma. Okay, so here goes. This is my rectangle made of two hyperbolas, two confocal ellipses. And I consider trajectories which are tangent, which have the same caustic, the same confocal ellipse. So one of them is a diagonal. But if I move slightly here, I will have, and honest to God, quadrilateral. And then if I continue, I will arrive to another diagonal. So what I need to show is that this picture actually holds. So that's what you have. And the reason is what I said before. In the special coordinates on this confocal ellipse, the reflection in ellipse is given by parallel translation, and reflection in hyperbola is given by formula C minus T. So it's involution. So if you compose four such formulas, two parallel translations remain parallel translation, two involutions remain, position of two involutions is also parallel translation. So altogether it's parallel translation for every such trajectory, but there is one which is fixed, diagonal, the original diagonal. So they're all for periodic, and the rest is the same as for usual rectangle. So that's a proof, deduction of Ivory lemma from integrability of billiard inside ellipses. Actually, we can say more. Another 19th century theorem due to Schall, almost the same picture. So an ellipse, a confocal ellipse. Take 2 points on a confocal ellipse, draw 2 tangent lines from each one. Now we have 4 lines, and they make a quadrilateral. And the theorem is that this quadrilateral admits an inscribed circle. So it's a circumscribed quadrilateral. I'm going to prove this again using the same ingredients. So there are 4 points on this inner ellipse. You remember, every ellipse has special coordinates system. So the coordinates of these 4 points will be S1, S2, T1, and T2. Now, these ones. Points A and B are on the same confocal ellipse, which means that T1 minus S1, that's A, and T2 minus S2, that's B. The differences are the same. We can rewrite this as sum equal to sum, which means that C and D are on the same hyperbola, confocal hyperbola. That's step number 1. And now we need to use string construction. So F and G are 2 functions. Remember, going from point outside to point O one way and another way. So these are these 2 points, F and G. Yeah, it's written here. And we have F of A plus G of A equals F of B plus G of B. A and B are on the same confocal ellipse. F of C minus G of C equals F of D minus G of D on the same points. C and D are on the same confocal hyperbola. Now a little acrobatic with these formulas. I add them, or maybe subtract. Anyway, combine them, and remember what F and G mean: distances from a point to point O to 2 ways. And many things happen. What remains is this. And this is something about quadrilateral, which means that the sum of opposite sides are equal. AC plus BD equals AD plus CB. This is necessarily sufficient for inscribed circle to exist. So that's end of the proof of Schall theorem. And next thing is what is called Poncelet Grid. So Poncelet Grid is a name given to this picture by Richard Schwartz, who wrote the paper on this subject. Actually, it turned out that part of his theorem was known to Darboux, but not the hardest part. The hardest part was new. So let me explain what you see on this picture. Start with the Poncelet polygon on 2 confocal ellipses. So everything I do is on confocal ellipses because I'm thinking in terms of billiard. So in other words, consider n periodic billiard trajectory inside an ellipse, or equivalent to Poncelet n gone. Let's say it's a simple n gone, although we can start with a star shape. That doesn't matter. This n gone is not visible. It's somewhere near this inner ellipse, but it's a Poncelet polygon, so it's tangent. It has inscribed ellipse and circumscribed confocal ellipse. Consider its sides and label them, let's say, counterclockwise. So side 1, side 2, side 3, and so on. There are altogether n sides. So that is, there are n lines, and these lines intersect. So there are roughly n squared over 2 points. Actually, n plus 1 choose 2 points. And they form a fine set of points, which is called Poncelet Grid. This picture can be viewed in 2 different ways. On the one hand, you can partition this set of roughly n squared over 2 points into concentric subsets, which are also finite. And you see this concentric subsets here. Actually, they lie on confocal ellipses, but that's part of the theorem. So far, I'm explaining the picture. And so here's a formal definition of concentric subsets. So the indices have fixed difference. And then you can also view this as radial subsets. This, and so on. They lie on confocal hyperbolas, but that will be also part of the formulation of the next slide. But here is a formal definition. These are intersections of lines whose indices sum up to a constant. So there are 2 ways to view this picture. Is a union of concentric subsets denoted by P sub k and radial subsets denoted by Q sub k. And now the formulation of the theorem. So I say Darboux-Schwarz. In this formulation, n is odd. For n even, Richard didn't bother to write down the formulation. The first 2 statements hold for every n, but the last and the hardest one literally is true for odd n, and for even n, slightly different statement. I don't have time to go into this, but the statements are concentric sets lie on nested ellipses. Radial sets lie on disjoint, also nested in a sense, hyperbolas. The complexify versions of these conics have 4 common tangent lines. So in billiard language, they are just confocal. The theorem is more general than confocal, but this is a projective formulation. And finally, this is the strongest statement, which Darboux didn't have. All concentric sets are projectively equivalent, and all radial sets are projectively equivalent to each other. So this is a very strong statement, really. You have a huge set, roughly n points. I mean, two sets consist of n points, and they're projectively equivalent. So all cross ratios involved are equal. And here's the proof. I hope you're not too tired of proofs, but still 20 minutes to go. Okay, so again, I will use the same coordinates which come from Arnold and integrability on the innermost ellipse, the one which is tangent to that set of lines, to that Poncelet and gone. So in these coordinates, we can choose the origin appropriately, and then the coordinates of the points involved will be 0 and 1/n and 2/n and so on up to n minus 1 over n. There are n points which are equally distributed in this coordinate system. And the string coordinates, remember, every point outside has 2 coordinates, which are coordinates of the tangency points if you draw 2 tangents. The string coordinates of the points of the set P sub k are this number. So it's the first one is 0 k over n. The second one is 1 over a, k plus 1 over n, because the difference is k over n, and so on. And maybe I should get back to the picture to make it more clear. So, for example, this line, and then next one, this line and this line. We just changed the coordinate of the tangency points by the same quantity. And that means that this set pk lies on a confocal ellipse. The difference remains the same, and that's the description of confocal ellipses in this coordinate system. And the same argument works for radial sets. Keep it. But that's only the explanation of the first two statements. The last and strongest statement needs a little more, and it's another lemma by Ivory, which is very easy to prove by direct computation, and it's also an interesting statement. So suppose we have two confocal ellipses which are centered at the origin and have axes which are aligned with the coordinate axis, so in the standard position. And then there is a linear transformation which takes one to another. It's called A here. It's given by a diagonal matrix which scales in the direction of both axes and makes one into another. So the statement is that this linear transformation takes every point of one ellipse to a point of the other one, which lies on the same confocal hyperbola. So point P of small gamma and its image of in capital gamma A of P, they lie on a confocal hyperbola. Okay, so the claim, which finishes the proof of this Poncelet Grid theorem, is that that very linear transformation, which exists because of that either Ivory lemma, takes one concentric set to another concentric set, or to its centrally symmetric one. This depends on whether the difference of these indices is even or odd. And here's the proof, but maybe you are kind of tired of the proof, so it's proof in the same coordinates. Maybe I'll skip this to give you a little rest. But instead, I'll show you what happens if we combine this with Schall theorem. So remember, every quadrilateral involved has an inscribed circle, and that's what we get, a very interesting circle pattern. So this works only, this is not projectively invariant. This is Euclidean statement. Circles are not invariant under projective transformation. So the inner polygon is really a Poncelet polygon on confocal ellipses. So this is one picture, and here is another picture which I borrowed from a paper by Agapian and Babenko, recent paper on in circular nets. So here you have a much more fine picture, but it's the same. So plenty of confocal ellipses, all confocal to this one, some confocal hyperbolas, and this circle pattern. Okay, next topic. Configuration theorems which come from complete integrability of billiard inside ellipsoids. Actually, complete integrability is a rare situation, but it's usually means a lot of consequences. You already saw some billiard transformations commute, and this is another manifestation of this miracle of integrability. So what do you see in this picture? You see inside this green heptagon, it's 7-gon, and this is Poncelet. I didn't, not to make it too busy, I did not write the circumscribed and inscribed ellipses here. But trust me, this little heptagon is Poncelet. Now we do the following. We extend its sides, and we intersect sides skipping one to obtain the blue heptagon. So this side, next one will be this one. I skip it and I take the next one. So skipping one side, intersecting them cyclically, we create a new blue pentagon. And the green pentagon is constructed the same way, but now I skip two. So this side, I skip this two and intersect with this side, get this point. So I start with a little heptagon inside, Poncelet heptagon inside, and constructed blue and green heptagons. Now I do same things with blue and green ones. With the blue, I intersect sides, skipping two. This side, I skip this, intersect with this one. And in the green one, I intersect sides, skipping one. So this is side, this I skip and intersect with this one. And you see, I get to the same point. So the outer red heptagon is obtained in two different ways. It's a configuration theorem. So there are two procedures and they yield the same result. Okay. This is the last theorem I want to prove. So 7 here is odd. My proof will use this fact. For even gons is also true, but the proof is more complicated and I actually don't have it completely written yet. But it's notation. So P is this inner green one. B, G, and R, blue and red, are the other 3. And now the argument, which takes one slide. So what do we have here? We have here two operations, which I described: intersecting sides skipping one side, intersecting sides skipping two sides. They are denoted by phi and psi, and phi skipping one side takes inner to blue, phi takes inner to green. We also have two projective transformations, or two linear transformations if we start with confocal ellipses, the ones given by Ivory lemma. Remember, Ivory says that if you have two ellipses which are aligned to axis and centered at the origin, there is a linear transformation which takes one to another. And here we have two such transformations, F and G, which take the inner one to blue and to green. And the essential thing is that these two linear transformations commute because both are given by diagonal matrices. Okay. Another essential thing is that linear operations or projective operations and these combinatorial operations also commute. If you intersect two lines and apply a transformation, you can do it in any order. First transform, then intersect. Okay. All right. So the rest is just a little algebra. F composed with G applied to P is F applied to G because G of P is capital G. But capital G is also phi of P. So this now phi and no, it's psi. Psi and F commute, but F of P is B. So left-hand side equals psi of B. The second line is very similar, but instead of F, I start with G. Instead of G, I have F here. And the same argument yields on the right phi of G. But these two gentlemen are equal. So these two gentlemen are equal, and that's precisely the statement. You get to red one in two different ways, and the result is the same. End of proof. And I'm not an expert on configurations, but what I learned collaborating, you'll have names of my collaborators. The next slide, or maybe one after the next. Actually, people working on configuration theorems, they had similar pictures, starting with a regular polygon inside. And there was a big question whether such configurations were flexible. I mean, you always can apply projective transformation because everything inside is points, lines, and conics. But there was a big question whether they're flexible. Now we have the answer. You can start with any Poncelet polygon. Poncelet polygons are not projectively equivalent to each other. So we actually have, as a byproduct, solution to this problem. Here's a picture which involves 8 points. So this is octagon. I said that even n also works, but the proof is not completely written yet. It's a little bit more subtle. And this is a work in progress with 2 people working on configurations. That's how I learned about this science. And Richter Gebert, who is a master of projective geometry. He has the software called Cinderella. All pictures, by the way, you see are done in Cinderella. And he has a book on modern projective geometry as well. So this is a picture with 8. And I'll show you slightly more complicated pictures just to impress you. I don't know how many, 17 maybe. It's a good picture for a tattoo maybe. And of course, you can have more, that's not yet. You can modify the construction. You don't have to consider consecutive lines. You can label lines secretly, but not necessarily consecutively. So first, skip something, second, skip the same thing. And you can also, I didn't want to show you too many, but you can also combine this. Once you have this theorem which involves 4 layers, so inner and then blue, green, and red, you can actually iterate this construction and have many layers, so some kind of grid of configurations. Okay, a remark is some of you probably heard of pentagram map. Pentagram map is another invention or discovery of Ray Schwartz. It's quite a popular subject these days. It's a discrete, completely integrable system, again, based on a very elementary construction of projective geometry. It works as follows. So you consider n-gon in projective plane. Polygons are considered only modular projective equivalents. So 2 polygons are the same if they are related by projective summation. And then what you do is you connect vertices by short diagonals, combinatorially short. So you skip one vertex. So this point connects to this connects to this, and so on. And the intersection of these diagonals form a new polygon. So in this picture, red becomes green. And that's the map. It's called pentagram map because 5 is first time you can do it. Actually, it's not a very good name because for 5, the result is identity map. For 6 is second iteration is identity, but starting with 7, it's actually genuine map. And it's known to be completely integrable. It's known to be connected to the theory of cluster algebras. It's a good stuff, but it's not for this talk. But a remark that configuration theorem, which I just showed you, shows that this pentagram style maps using deeper diagonals commute. If you start with a Poncelet polygon, and for example, in this picture, you use short diagonal map and skip 2 diagonal map and do them in 2 different orders, the result is the same. It's just another interpretation of this configuration theorem, which may be of interest to people working in a different field. Okay, I have something like 6 minutes, but maybe I don't need that much. This is the last chapter of my talk. Just to convince you that this subject is evergreen, let me introduce Dan Reznik. So, Dan is an engineer who graduated from Berkeley, and he worked in California capturing solar energy. And then they sold their startup to, I think, General Electric. He's Brazilian, so he returned to Brazil, and now he has some time, apparently some money to live on, and he does many things. Right now, he's writing comments to Don Quixote, but before that, he spent several years experimenting with Poncelet theorem and billiards and ellipses and such things. And he and his collaborators, they discovered, I don't remember exactly, something like 60 properties, unknown properties of billiards inside ellipses. Most of them are still conjectural, I mean, computerly established, experimental, but some of them are theorems. And I will just refer to 2 papers in which I participated. These are 2 references, and I'll show you the 2 theorems among many which he discovered. And this will be without proofs, so don't worry. The first theorem concerns n-periodic billiard trajectories in an ellipse. So what you see here is a 5-periodic trajectory, and it concerns the angles of such a periodic polygon. So the Poncelet theorem says that if you have or integrability, if you wish, says that if you have one such periodic trajectory, then you have one parameter family. And so in this one parameter family, all properties of these polygons will change. And the question is, how do they change? And one of the answers is given by this result, that the sum of cosines of these angles remains the same in this one parameter family. And actually, we know what it equals to. It equals to the value of Johan's style integral, remember at the very beginning, times the perimeter of this polygon minus n. N is period. So this is one of the results he discovered experimentally, and this is proved in the 2 papers I mentioned in different ways. in the second paper with Billiards proved using his non-traditional generating function, which is useful, I think, it seems. And here's another theorem which was discovered by Reznik and proved by other people. So again, start with the n-periodic trajectory and now extend the tangent lines to the ellipse at the impact points, and you get a circumscribed n-gon. And it also has angles. And again, everything is in one parameter family. So what about these angles? Here's what. The product of cosines remains constant in this family. And Reznik has many similar observations, and most of them are still open. If you have some time to kill, you're welcome. They're published. In arXiv, you'll find many papers, and that's all I want to say. Thank you.
So the billiard on the surface of a sphere with circles will be integrable.
With conics as well.
Conics as well.
Yes, but of course one needs to define a conic. It's intersection of quadratic cone with a sphere. Yes.
And hyperbolic plane, anything like that?
Also, yes.
The same.
Yes. Actually, yeah, I forgot. Since I actually had a minute, I should have said it. A generalization of everything you saw here is, as you mentioned, of course, spherical and hyperbolic geometry, but actually a much greater class of metrics is Liouville metrics. So, for example, instead of a sphere, we consider an ellipsoid and induced metric from the ambient space, and there will be an analog of confocal conics. This will be lines of curvature. In other words, intersections with confocal quadratic surfaces. In dimension 3, there are 3 kinds. There is an ellipsoid, there is hyperboloid of 2 sheets, and hyperboloid of 1 sheet. So when you intersect this confocal family with the given ellipsoid, you will have a grid of curves. These are curvature curves on the ellipsoid, and they play the role of confocal conics in the plane. And everything I said, you can play billiards using geodesics. Almost everything I said extends, except for maybe this Poncelet grid of circles. I don't know about circles. It will be still true that the sum of opposite sides of quadrilaterals are equal, but that's probably not related to having circles. But that's the natural setup for this kind of.
I think that these results have shown at the end that they come from the homogeneous scheme. So basically, there's some conserved quantity that you've shown. So maybe there exists some kind of meta integrable system for which these are first integrals.
They're all, yeah, I don't know. Short answer, I don't know, but here is some comment. It's a two-dimensional dynamical system which is integrable. So all integrals are functionally dependent on each other. So everything in this long list of Reznik's identities should fall into this category, but it doesn't tell you how to relate it. I mean, the first theorem I showed you actually gave the answer. It's Joachim-Stahl times perimeter minus period. That's already some work to do.
There is some algebra there.
There is some algebra, but I don't know any systematic approach to this. The reason I showed you this too, just to impress you, what kind of things are hidden, and apparently no one knew that the product of cosines is the same in this one parameter family. But yes, in a sense, it's not really interesting because they're all functions of each other. But maybe it is interesting. I don't know.
Reznik also found some identities for outer billiards or other kinds of billiards?
Well, with outer billiards in the plane, I mean Euclidean affine plane, the only integral case we know is again an ellipse, but because it's affine invariant, it's the same as a circle. For circle, everything trivializes. You can just calculate.
Question was if you have an equivalent of the spin construction to get.
Yes, that's a very good question. There is an analog of string construction, which is called area construction. So thank you for asking. Actually, there is a better joke. So suppose we play this game of outer billiards. So a point X goes to point Y. The two attention segments are equal, and a role of caustic is played by invariant curves. And the question is, suppose I erase the billiard curve, only give you an invariant curve. Can you reconstruct the table from invariant curve? That's the same question. And the answer is yes. What we need to do is to consider one parameter family of lines which cut off fixed area. So that's an analog of string construction. They will envelop the table. And again, it's one parameter family construction. When you choose this area, you get family. If you change the area, you get another. So one invariant curve gives you one parameter family of tables. That's an analog. And by the way, it's a nice exercise again for your calculus students to show that the envelope bisects every tangent line.
There's the construction. You have two different things with the same, no, one caustic and two different.
One caustic and?
Like, could you have the outer curve not being a circle on each side? I know that there is a circle outside with the
Well, KM theory still applies. So for any oval, you will have invariant curves sufficiently close to it and also sufficiently far away. This is Lazutkin style. I mean, it's more due to Moser, actually, Moser and Doady. Yeah, also there is a theorem, a recent theorem by Belli, which says that integrability holds only for ellipses. That's
yeah, but I'm only asking for like
just
for some amount of area. Like if you know that for the delta area you have the caustic inside is a circle. Can you have another curve outside?
You mean circle, a real geometrical circle?
Yeah, because it will be ellipse or circle is the same, right?
Yeah, I think if it's an ellipse, if it's a circle, then everything should be a circle. It's, you can go back. Yeah, and I understand. I think it's true. I will not put all my money on it, but I think it's true. Yes.
Any other questions?
Maybe a quick. I probably should know this, but with the Poncelet sequence, you mapped it all to confocal pairs of ellipses, right? And so the only invariant is the eccentricity.
If you wish, yes.
I'm just thinking. So I presume that the closed polygons form a set of measures zero as far as the values of the eccentricity. Is it denumerable?
Who is it?
The set of values of the eccentricity of the confocal thing is that those for which is closed. Is that denumerable?
Okay, so there is an answer to this question, which is due to Kelly. It's a slightly more general question, not about confocal necessarily, but for two nested ellipses, for example. The question is when you have n-periodic Poncelet. And the answer is given, the theorem by Kelly. So you cook a certain matrix out of coefficients. I mean, two conics are given by two symmetric 3x3 matrices. You cook a certain matrix of rank n-ish, maybe give or take a little, and its determinant equals 0 if and only if n-gon closes up. So it's very rare, and there is an explicit algebraic criterion for it. It's called Kelly criterion.
It's just lower dimension.
Yes. Well, again, the numeral up to what? I mean, you can always apply projective transformation to it. You want to normalize somehow.
Just Poncelet polygons, which flows, the set of configurations, whenever you take this close line, the subset for which it closes.
No, the set of pairs of conics for which this game yields n-periodic trajectories, so there is an n-periodic and Poncelet and gone on them. This is proper subset. It's algebraic subvariety in low dimensional. Yes, in the variety of pairs of conics. Yes, but it's not. No, I think it's a subvariety.
Well, I was
it's not countable.
The projective transformation to appear vocal.
Yes, you can do that.
It's a confocal, then it's rational caustics.
No, the two ellipses have the same pulse line. That's what we do.
Yeah.
Yes.
Then it's countable because we're talking about rational caustics.
Rotation number.
Yeah.
Yes, for every well, that's what I'm saying. What do you want to count? Yeah, for every rotation number p, q, there is a unique.
Well, it is an order. If you take just the eccentricities out of order, you could ask it.
Yeah, I'm not sure whether it should be yes or no, but I think the situation is fairly clear. So if for example, we stick to my setup, billiards inside ellipses, for every two numbers, I mean, period and rotation number, there is a unique confocal caustic for that. And then you have one parameter family of such polygons. That's the situation. It's kind of normalization. We do not apply further projective transformations, just confocal family with fixed foci.
So in optics, there is kind of a generalization of the billiard with reflection, which these are systems where you've got sort of two materials, one inside another, and then there is reflection and refraction. And
Snell law?
yeah. And it's sort of supposed to be, there is some sort of mixing of energy between the two. It's supposed to be sort of more mixing energy than just the usual billiard. But I wonder if there is any kind of integrability for maybe some special things inside. But it's just, is there anything interesting from your point of view for this? Things where you got Snell things?
Well, I'm afraid I will answer with a question, which is not the right way to do it. But first, something about Snell's law. So Snell's law tells you what happens when you go from one medium to another medium where the speed of light differs. And the law is that the angles are not equal, but the ratio of sines or cosine depends on with what equals the ratio of speeds of light in this medium. And this is not a symplectic transformation anymore, but it's conformal symplectic. It multiplies this area form by a constant which is related to this ratio of speeds. So unless you return back to the same medium and the product of these coefficients somehow is one, it's not going to be area preserving. It's not Hamiltonian. So
there is some sort of conservation law because the energy is sort of distributed between reflection and refraction, and
right.
To one. But it becomes sort of fractal because you have, so sometimes it's called branching billiard. So the branch and
well, maybe you can teach me, but I want to say two more things which are more like questions than answers. So one is that I learned from physicists some 10 years ago that now they can make materials where the Snell coefficient is equal to -1. Yeah. So so instead of having this picture, you have this picture. Angles are equal, but you go that way. Yes, they can manufacture this kind of materials. And apparently it's very good for optics. Some optical properties are much better, perfect lenses. I'm talking about things I don't know. But what I know is that, of course, you can study this purely mathematically. And this is a subfield now in the study of billiards, which is called tiling billiards. So you consider a tiling of the plane, polygonal tile, and you start your trajectory, and each time you go from one tile to another, you do that. Okay, so this is area preserving, by the way. It's if you care about such things, but the question is what happens with trajectories. And for trivial tilings like square grid, the answer is very easy. There are exactly two behaviors. Either it's for periodic, you go like that, or it's infinite, but also periodic, like zigzag to infinity. But change the tiling a bit, and the situation becomes very, very non-trivial. So, for example, a very regular tiling consists of conical hexagons and equilateral triangles. Oftentimes see bathrooms on the floor. That's already very interesting. There are trajectories, there are some results, and there are some computer results. There are trajectories which go very far away, return back, go further, go back, very strange behavior. And of course, you can ask, take Penrose tiling, or take this Einstein tiling, for example, tiling a periodic triangle with one polygon, which is heptagon, actually. It's called hat. What happens there? I don't think anyone experienced it, but someone should. It's going to be interesting. But I know I'm not answering your question, rather asking my question.